So this is the first of 3 videos on for chapter 11 in the 5th edition of TRO, and this one is the beginning of the discussion on VSEPR structures. And we start by just talking about the fact that there are 5 geometries, 5 basic geometries that are observed in molecules, and they're listed here: linear, trigonal planar, also called planar triangular, tetrahedral, trigonal bipyramidal, and octahedral. Excuse me. So the first thing I want to do is show you each one, talk about how to draw them, what the bond angles are on them, and so on. So I'll go quickly through this. This is a linear geometry, and this is where you're going to have 3 or more atoms in a linear orientation, and the bond angle, the bond angle, so you have the chlorine, beryllium, chlorine bond, and our angle, I should say, the angle here is 180 degrees, linear geometry. All right, trigonal planar or planar triangular. You start with these 3 groups of electrons here, and the idea with these shapes is that, and this is the VSEPR theory, that they need to be as far apart as possible. So what is the geometry that will take those 3 bonds and make them as far apart as possible? And that's because you have electrons here that are repelling electrons here. And so what is the geometry that the molecule can accommodate so that there's minimum repulsions between the pairs of electrons in the bonds? So the bond angles here are 120, associated with 3 groups of electrons. Next one is tetrahedral, and you start out with a Lewis structure with right angle geometry. And then, how will those electron pairs minimize the repulsion between them, all 4 of them? And it turns out it's a tetrahedral geometry. This is a good representation of it here. This bond angle, which is the same all the way around, is 109.5. Now, next slide, you see the tetrahedron again, and this time it's contained within the tetrahedral pyramid. Notice this is a 1, 2, 3, and then there's another one in the back. So this is a 4-sided pyramid with equal lengths and sides. And so when the hydrogens fill into the corners of the pyramid, what is the bond angle? It's 109.5. So this is another way to look at it. Drawing. Go back and look at it for a second. The way it's done in this diagram is this hydrogen is up and this one is, these 2 are kind of in the plane, and then these 2 are out of the plane. I draw it a little bit differently drawing it. So if you have, carbon, if you look at this drawing, and a lot of people do it this way. So I put 2 of the CH bonds in the plane. One of them is coming out. So that's what that triangle means, and one of them is going back. So it doesn't look like it, but this is the tetrahedral geometry with 109.5 degrees. Also, all right, the next one is trigonal bipyramid. And here you have, I'm not going to read all this stuff, let's just look at it. So you have, this figure on the left here is good. So you have, these are 2 4-sided pyramids that share a common face. So the first pyramid is 1, 2, 3, and the base is here. The second pyramid has, one of the common faces is the base, and then you have 1, 2, and 3. So there's 2 pyramids that share this common face. Now take away all those red lines, and you get a very different picture here you have a triangle like this, and then one above and one below. So 3 of the bonds are in the plane of the triangle, and one is above and one's below. The bond, I'm going to draw it the way I like it. So, whoops, you draw a triangle, and then put in the bonds. The triangle just, helps to give you the shape. That's not the bonds. The bonds, in fact, it's a good idea since we have different colors. The bonds are in red. The triangle just gives it a little bit of structure. So these 3 are in the plane of the triangle here, and those are 120 degrees. Then you have one above and one below that plane. Now think about this triangle here as being perpendicular to the plane that I'm drawing in. So if you could see my hand, you might be able to see it. So these 2 lines are, in the plane, and then this triangle is 90 degrees rotated. So in other words, you've got 90 degrees between this bond and the plane. Underneath, again, you've got 90 degrees between this bond and the plane. And then you could say overall, there's a 180 degree bond between this one and this one. So anyway, I do use that drawing all the time when I'm drawing this shape. So it's a trigonal and it's a bipyramid. Trigonal means 3 legs, and then it's a bipyramid. So that's good to remember that. All right, the last one is octahedral geometry. And you can see here it's similar in the sense that it's 2 pyramids. This time the common face is a square as opposed to a triangle. And notice that there were 5 in the last example. There are 6 groups of electrons for this structure. So these are, you got the base plus 1, 2, the one behind 3, 4. So there are 2 5-sided pyramids that share a common face or a common plane. So let's see, in the example, the SF, you get the lone pairs. We're going to do all this in detail here. So so I guess if you get rid of the triangles, it ends up looking like that. I tend to do it this way. My square is a little bit off angle. And then, so my bonds, that was SF6. I've got the SF bonds in red. The green is just giving me a little bit of shape for my square there. And then one above and one below. And so bond angles here are 90 degrees. Every single bond angle is 90 degrees in this system. All right, so those are the five geometries. And now we've got some detail here. This is a scheme. I got 2 of them. I like the first one because you see that there are lone pair electrons in some of these representations. I like it with a little lobe. It looks like a little rabbit ear. I like the look of that, and I tend to draw it that way. All right, so what is this now? You've got, if you look in this column, you see the 5 shapes that I just showed you. So you have the linear geometry. This is the trigonal planar with the 120. This is the tetrahedral with 109. This one is the trigonal bipyramid. Remember, so that's the triangle, and then you get one above and one below. And then this one is the square here for the plane contained within the octahedral shape. So you got one above and one below. All right, now in molecules, you can come up with these shapes if you say, okay, I got two groups of electrons, 3 groups of electrons, 4 groups of electrons, and so on. In this column, you've got the same situation where you have 1, 2, 3 groups of electrons, but that third group is a lone pair as opposed to a bond. Otherwise, there's not a lot of difference. So here's just one lone pair instead of a bond. Put it here, here. And then in this case, next example, you got two lone pairs. This would be like water. Two lone pairs, two lone pairs. And then over here you got 3 and 3 and 4. So you can see how this can get generated. Now also, when I use the term pairs of electrons or groups of electrons, not pairs, but groups of electrons. So in this case, there's 4 groups of electrons. That can be a single bond, a double bond, a triple bond, or a lone pair. And I'll show you examples for that. As you can see, they're similar. And the next one, it's just got, you know, a line with 2 lone pairs, but it's the same. It's the same thing. All right, on the next one, similar. One difference is it's got the names of the shapes on it, and you are going to have to learn all these shapes. So you got linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. In this case, you've got bent, and the names come from the bonds, so you ignore the lone pair, and then you just say, well, that's bent or angular. If you ignore this lone pair, you've got 3 here, so it's a trigonal pyramid. I'm going to draw these and talk about each one, so let's go ahead and do that. Alright, so what I want to do is go through each one of these and learn all the details. So I've got to have my list somewhere here. Let me see. CO2, BF3, water. Okay, so I do have my list here. So I'm just going to start with a clean slate here, a clean board. And first we're going to look at beryllium, BeH2. All right, what do we know about beryllium? Beryllium, if you look in the periodic table, it's in group 2. And the electron configuration is 1s2, 2s2. So there are 2 electrons in the valence shell. And if you remember, that was one of the exceptions to the octet rule. Remember, beryllium and boron were exceptions. So beryllium then has 2 groups of electrons, or it's got 2 electrons, I should say, not groups. It's got 2 electrons. And it can make 2 bonds, so hydrogen in this example. You can put little X's there, whatever you want to do, it's fine. So the Lewis structure then is like this. Now it turns out for this example that the VSEPR structure is the same as the Lewis structure. And by the way, VSEPR, I've described it, but it stands for valence shell, electron pair, repulsion theory. VSEPR. So that's where the electrons are going to assume some geometry that will allow for minimum repulsions between the bonds. All right, whenever you want to come up with your VSEPR structure, you always have to start with your Lewis structure. In this case, because there are no lone pairs in it, all you got are those 2 groups of electrons in the BeH bonds, and so they're going to be as far apart as possible the way I did it. So there's no difference in this case between, the Lewis and the VSEPR geometries. So this one's simple. Next one is BF3. Boron is another exception. So boron is 1s2, 2s2, 2p1. And the valence shell, there's 3 electrons. The Lewis structure, remember you can just make right angles, no big deal. It's less than 8, there's 6 for boron. So that's your Lewis structure. Your VSEPR structure says, okay, how many groups of electrons do I have? And the answer is 3. What's the geometry that's going to make them as far apart as possible? So that bond angle is 120 degrees, and the name of the shape is planar triangular. All right, the next one is NO2 minus. And this is a good example for a lot of reasons here. Count the electrons first. You get 5 plus 2 times 6, plus you want to add 1 for the additional electron. So that is going to be 12 plus 6. This is an 18 electron system. And when you draw the Lewis structure, you're going to put the negative charge, that extra electron, you're going to put it around the central atom, nitrogen in this case. So it's 1, 2, 3, 4, 5 for nitrogen. And one more, which is the electron, the electron in question. So let's see, I know how this is going to turn out. It's probably best to move this over here. So let me do this like that. There's 6. Okay, come in with the oxygen. Each oxygen has 6. And then that's basically correct, except for the fact, let me get rid of that, except for the fact that you don't have the octet for the central atom, right? The rules for the Lewis structures are that you have to take care of the atoms on the outside first, then you take care of your central atom. So the oxygen has 8, but the nitrogen's only got 6, so you know what to do. We're going to take a pair of electrons, move it in, make a double bond, and in this case, there's 2 ways to do it. So that means there's going to be 2 resonance structures. So let me put that up top here, a little bit more room. So you're going to have double bond on the right. Then there's a resonance, where the double bond is on the left. And you want to put a negative right there. All right, so now this is the Lewis structure, and I'm going to erase this drawing below it. I need more room. I thought it was. It's interesting. There we go. Okay. Oh, I think I know how that eraser works now. All right, and I forgot one more thing. The lone pairs are there as well. So this is a good example. First of all, it's a resonance, has resonance structures, but also you ask the question, how many groups of electrons are on the central atom? It's 1, 2, and 3. The single bond, the lone pair, and the double bond, all groups of electrons. So this system has 3 groups of electrons around the central atom. And so you look in the table, or you've got it memorized. The shape is going to be planar triangular shape. And that's not the name of the shape. That's just how you're going to draw it. Okay. So you would do this. Rabbit ears. This is supposed to be around 120 degrees. All right, and that is the VSEPR shape. What we're going to find in general, because these electrons are not bound to an atom here, that the electron pair is a little bit larger in volume than when they are bonded to two atoms. So this is big. It tends to push the two bonds away because of its size, which makes them closer together here. So the bond angle is going to be a little bit less than 120 degrees. For the case of the planar triangular, I will accept 120 degrees. Don't worry, it is less than that. You could put the less in there if you wanted to, but 120 works for me. Okay. Now the name of the shape is not planar triangular. You ignore the lone pair and you just say it's bent or angular. So you just look at the bonds and say, okay, what's the geometry? All right, and the name, the answer is it's bent. So you're going to need to know the bond angles. You're going to be able to draw it, and I have no idea how I'm going to test you on it. And then the name of the shape as well. Okay, so that's NO2 minus. The next one is methane. And we've been through the Lewis structure on that several times already. All right, now you need the Lewis structure to ask the question, how many groups of electrons are there? And the answer is 4. Now you know that it's going to be tetrahedral geometry because 4 groups of electrons do that. They form that 109 degrees. So as I said, I put 2 of them in the plane and 2 of them. This one's coming towards me out of the plane, and then this one's going away from me. It's like behind the board there. All right, and no matter how you try, it's pretty much impossible to depict that. The bond angle here is 109.5, and the name of the shape is tetrahedral. Okay, so then ammonia is next. And Lewis structure for ammonia. Nitrogen has 5. Hydrogens each have 1, so that's going to make octet for nitrogen. And question is how many groups of electrons? So the question is how many groups of electrons? And the answer is 4. You include the lone pair. So 2, therefore, it's you draw it as a tetrahedral. Okay, so that's over here. Now again, my lone pair I put in the plane of the board here. Same with the other NH bond. Then one of them is coming out and one of them is going back. Okay, so you draw it that way. 3, what are the bond angles? And in this case, it's 107. So how does that work? You've got this lone pair that's pushing the bonds closer together, closing the angle. It's going from 109.5 in a pure tetrahedron to 107. Excuse me. 107 for this particular one. All right, the name of the shape is not tetrahedral. It's based on the fact that there are 3 bonds there, and it's called pyramidal. And I think in that table it might be trigonal pyramid. Yeah, that's right. I always forget that one. Trigonal trigonal pyramidal. I'll just say trigonal pyramid. Okay, now also there's another name for it. I've had the model, you'd be able to see it, but it's also called the umbrella shape. Yeah, I can't even describe it without the model. But if you're holding the umbrella here, these things are kind of flipped away from this plane of perpendicular, which is perpendicular. And so they're flipped out this way. And it's like an umbrella that you've been holding in the wind and the rain, and the umbrella has flipped inside out. And then the next instant they come down. And the umbrella kind of flips back and forth. There's evidence for it experimentally that it's like that, and the umbrella actually flips back and forth. So someday I'll show that to you. So umbrella is the other name for it. All right, so then you see what we did there. The name's not tetrahedral. It's based on the fact that there are 3 bonds and they have to be in this particular geometry. All right, if I forgot something, I'll have to come back there and remind you. All right, the next one is H2O in this set. And the Lewis structure. You always start with the Lewis structure. This one, oxygen has 2 lone pairs. All right, then you say how many groups of electrons? There's 4 groups of electrons. Therefore, you draw it as a tetrahedral, or tetrahedron, I guess. And then in this case, I like to put the 2 lone pairs in the plane. It's just easier for me. This OH bond is coming up towards me, and this OH bond is going away from me. And again, if I had models, you could see that hard to do it. There's 2 planes in this molecule. One is one is this plane right here, and the OH bonds are in it. And then, or the other way, you could say these lone pairs are in this plane of the whiteboard. And then this plane here is 90 degrees turned, and so you have 2 planes that are 90 degrees to each other. Don't worry about that. It's too hard to see. All right. Now you're gonna the bond angle here is gonna be even smaller than the 107. Okay, in this case, you got 2 lone pairs that are pushing the bonds together. So this is 104.5. And then the name of the shape is just based on the bonds, so it's similar to one we saw earlier, and we're going to call it bent. Which one was it? It was NO2 minus had the bent shape as well. Okay, now there are these different categories associated with how many groups of electrons. We've done 2 groups, 3 groups, and 4 groups. I'm fine if you just use the bond angles for the main molecule in the group, or the first molecule in the group. In other words, if there's 2 groups of electrons, well, that's going to be linear. If there's 3 and it's something like NO2 minus, I'm fine with you saying that the bond angle is the same as that of BF3. In this case, methane, ammonia, and water. So this is like the 3rd set here, the tetrahedral geometry set. And I want you to know these different bond angles. So for the first one, it's 109.5. For the ammonia, it's 107. And for water, it's 104.5. So this is all within a group, and you could say, yeah, they're all 109.5, but I want you to know these differences. Later on, this is an example that comes up in tests. You know, you might be your MCAT or your DAT exam, these numbers, I don't know why, but, people seem to think that's a good test question. So that's why I want you to know that for this set. That's the only set I'm concerned with regarding that. All right, the next set then is 5 groups of electrons. Okay, and for this one, we will start with PCl5. And if you remember, I said that elements in period 3 or higher can have more than 8 electrons around the central atom. This is a case like that. So phosphorus is underneath nitrogen in the periodic table. It's got the same number of valence electrons, but it can have 8, 10, or 12. In this case, you're probably not going to see 12, but it can have greater than 8 or greater. So you start out with your Lewis structure. There's 5 electrons in the valence shell. 1, 2, 3, 4, 5. So think of the configuration. It's 1s2, 2s2, 6, 3s2, 3p3. Okay, there's 5 electrons in the valence shell. Then I tend to just kind of, I'm not looking for right angles because we know that in this case there's going to be 5 bonds. All right, and then you're going to have chlorine, 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 chlorine. And so the chlorine can form one electron with this bond. These 2 electrons can form a bond. Then chlorine's got 6 more. Right, so that's the one that forms the bond, and then there's 3 lone pairs. Seven electrons for chlorine. So that's good enough. I mean, you don't have to put in these black dots here, but you can just put the bonds there. Lewis structure. All right, now you ask the question, how many groups of electrons? In this example, it's got 5, and so 5 is that trigonal bipyramidal structure. So the VSEPR structure then, draw the triangle just to give a little bit of shape. Now this triangle is not in the plane of the whiteboard, it's perpendicular to it. So then the actual bonds, whoops, I'll do that in black. 3 of them are in the corners of the triangle. Then 1 is above, I made it a little bit longer, but it's not, and 1 is below, like that. Okay. So this has 120-degree angles, and don't worry about the variations for this set. Since the triangle is perpendicular, this chlorine coming down right here is 90 degrees. This one is 90 degrees from the triangle. And then, of course, you've got the 180 as well. All right. And that is your VSEPR structure. The name of the shape is trigonal bipyramidal, or bipyramidal shape. You can say pyramid, that's fine. All right, got all your bond angles, the name of the shape, and for the one that's in the represents the main category, the name of the shape is the name of the category as well. All right, so then let's keep all these together. Trying to anyway, like that, and then move it up. So the next one in this set is SF4. And the Lewis structure, there's 6 electrons in the valence shell, 1, 2, 3, 4, 5, 6. And when I make the bonds, I put them all next to each other. And the reason why I do that is it makes it easy to locate the lone pair. Okay, so this is an acceptable Lewis structure as far as I'm concerned. And now you want the geometry. You're going to get the VSEPR structure. There are 5 groups of electrons. And so start out drawing your triangle. You got sulfur in the middle. And now the question is, this is an interesting problem here. The question is, which one of these 2 structures is correct? So you can put 3 fluorines in the plane of the triangle. You can put one above and one below, like that. Actually, not one below, the lone pair goes below. Or you can put 2 SF bonds in the plane and the lone pair in the plane, and then 1 bond above and 1 bond below. So, which one is correct? Okay, so the answer is this one. This is the correct structure where there are one of the lone pairs is in the plane. That's the correct structure. So why? And the answer has to do with the number of 90-degree repulsions. So if you think about this triangle here, remember the bond angles are 120 degrees, right? And that's the geometry that is assumed in the triangle because that's the minimum repulsion, right? This fluorine SF bond is coming down and it's perpendicular to it, so there's a 90-degree here, right? And so the question is, this lone pair, how many 90-degree repulsions does it see? So in this case, I'm going to make a mess here. So this lone pair sees, that's not a good drawing. This lone pair sees a 90-degree repulsion to that. So in other words, the FS lone pair bond is right angle because the lone pair is perpendicular. The FS lone pair, that is also 90 degrees because this triangle is perpendicular. And then this FS lone pair, that's 90 degrees at all as well. So this is 3 90-degree repulsions. All right. Now in the other example, if it's in the plane, this is 1 90-degree repulsion. And this, I'll do a different color. This is the other one. No, that's not a good color. That's the other one. So this one has 2 90-degree repulsions. Therefore, there's less, I mean, you can talk about the 120-degree repulsions, but they're not as strongly repulsive as the 90-degree ones. So the big issue is the 90-degree repulsions. This one's only got 2, therefore it's lower in energy, and therefore it's the correct structure here. So that's a very interesting example there. And also the name of this one as well, the name of the VSEPR structure is seesaw. And a seesaw is something that the little kids play with in the park. They get on the seesaw and go up and down. And it's got this fulcrum here. And then this long plank. And the kids sit on it and play, right? And they can go up and down. So This molecule is similar to that in the sense that, and I have to look at this for a second. Okay, let me draw it again. So this is the long plank, and then this is the fulcrum here, and the kids can go back and forth. So this goes back and forth like that. So that's why it's called a seesaw. All right, so we got our bond angles, we got the name of the shape, we've got the overall geometry, we know which one is stable. So now we can look at the next one within this same group. All right, so the next example is ClF3. This happens to be one of my very favorite molecules. And chlorine 1, 2, 3, 4, 5, 6, 7 can make 1, 2, 3 bonds to fluorine. 2, 4, 6, 2, 4, 6. And then I put them together because it's easy for me to find the lone pairs. You don't want to have dots on the other side and then trying to hook them up. It's easier this way. All right, now how many, this is the Lewis structure. How many groups of electrons? So the answer is there are 5 groups. And therefore we're going to draw it as the trigonal bipyramid. My throat is in kind of bad shape here. All right, we're going to draw it as a trigonal bipyramid, and for the same reasons that we used before, we're going to put both of those lone pairs in the plane. And this is why I like this molecule, because it's got right angles. You just don't see molecules every day that have right angles. Right, so this is 90 degrees. That one's 90 degrees. Whoops. And that's a very pretty molecule. So the name of this shape is T-shaped. T-shape or T-shaped. And I think that's all for that one. There's one more in the group, and that one is I3 minus. So let's see. Let's go ahead and say 3 times 7 for each iodine plus 1, and that's going to be 22 electrons. So you can, you can start out putting them as far apart as you can write them at right angle as well. That would be fine for a Lewis structure, but you know how it's going to end up anyway. And then you go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And 2 more. So that's 22. Okay, that's going to be the Lewis structure. So you got 1, 2, 3 lone pairs around the central atom and 2 bonds. Okay, so it's got 5 groups of electrons, and we're going to draw it like a trigonal bipyramid. Whoops, not sulfur, iodine. We're going to put all 3 lone pairs in the plane. And then 1 bond is above and 1 bond is below. So the bond angle's here, 180 degrees. The name of the shape is linear. So you've drawn it as a tetrahedral bipyramid, but you're calling it the shape The shape is called the molecular, this is called the molecular geometry. This one is called the electron pair geometry. Right, so it's the geometry of the molecule. Well, that's messy. Molecular geometry. Well, that's messy too. Should not scrunch. Move it up and do it right. Okay, that's better. All right, so that is that group for five groups of electrons. This is the set, I should say, I guess, and you can't even see them anymore, but you can go back and blow them up. All right, and then the last set is going to be 6 groups of electrons. The first molecule is SF6. Lewis structure, 1, 2, 3, 4, 5, 6. Sulfur is right below oxygen in the periodic table, so it's got 6 valence electrons, and each fluorine contributes 1. Do you have to draw the lone pairs? Yes, you do. I have no idea how I'm going to test you on this. Get to that bridge when we get there, I guess. Cross it when we get there. Okay, so this is the octahedral, right? 6 groups of electrons. Octahedral geometry. Okay. And for this one, you draw that square. It's kind of a skewed square. Sulfur in the middle. You got 4 bonds in the square, 1 above and 1 below. Bond angles are 90 degrees, and the molecular geometry name is the same as the electron pair geometry name, which is octahedral. All right, all those bond lengths are the same. All of the bond angles are the same. All right, so within this set then, the next one is SCl5 minus. And let's see, so you got sulfur with 1, 2, 3, 4, 5, 6 valence electrons. You have 1 more because it's charged, so that makes it 2, 4, 6, 7. Now you got to make 1, 2, 3, 4, 5 bonds, and there'll be a lone pair. So there's 6 groups, 5 bonds, and a lone pair. So 6 groups of electrons, we're going to draw it as a octahedron, and then we're going to put the lone pair in. In the case of the square and the 90-degree geometry, it does not matter where you put this lone pair. Tend to write it on the bottom there, but you know, this molecule is rotational symmetry, so when you move it around, you could move it into the plane and it doesn't affect anything. Okay, and I got 1 more. Oops, that one. There's 5 chlorine bonds. And this got a negative charge, don't forget that. You can put it in brackets. All right, so this is called square pyramid. You draw it as an octahedron, You ignore the lone pair. You see you got well, let me write it down first. Square pyramidal or square pyramid is fine. And what I'm saying here, so you got the square base. And if you draw these red lines in, you can see the pyramid. All right, so 1, 2, 3, 4-sided pyramid going around, and then the extra side, so it's really a 5-sided pyramid. The base is a side as well. Don't put the red dashes in there. It gets too confusing, but it's kind of cool to see that you can really see this. You can view it as a pyramid. All right, don't worry about any slight changes in bond angle. 90 degrees works for me. Okay, now one more. I think the table's got some extra entries here, but I don't know of any examples like that. So this would be the last one as far as I'm concerned. And here is a molecule made of fluorines and xenon. I don't know if you've ever seen these molecules before, but there's a whole series of molecules made from xenon, which are not as stable as you would think. Xenon is not supposed to have any bonds at all, right? But these molecules were synthesized by a professor at UC Berkeley in the 60s, so they're pretty well known by now, but you wouldn't necessarily think that they could form. But anyway, as far as we're concerned, we have xenon with 8, making 1, 2, 3, 4 bonds to xenon, to fluorine. Okay, so it's got 6 groups of electrons. And we're going to draw it as an octahedron. And we can put all 4 of those bonds in the plane. Again, you don't have to, because of the 90-degree geometry here. And 1 lone pair above, 1 lone pair below. So just think of the bonds part of it, and you've got these molecules in a square. So this is a really interesting example as well. This one's called square planar. And again, the bond angle is good enough for me. They're 90 degrees. In fact, they are 90 degrees in this one. All right, now the next question is which molecules are polar? Now that we know the VSEPR structures, which molecules are polar? And we can just, don't have to do all of them, but we can look at a few of them. So for CO2, this molecule is linear. And we talked about this before. I showed you this before. So this has got a dipole pointing in this direction. You got another dipole pointing in that direction. So the net dipole moment is 0, and the molecule is nonpolar. All right, water, we looked at that one as well. So you got this bond angle here, if you remember, is 104.5 degrees. And this is the one that has the dipoles pointing that way and that way, which gives it an overall dipole moment pointing up. And so this molecule is going to be polar. The next one is SF6. All right, and so the question, this is an interesting question. Is it polar or non-polar? Fluorine is the most electronegative atom, and so the electrons are going in this direction. The individual dipole is pointing that way, but exactly 180 degrees opposite, you've got the same thing pointing in the opposite direction. Similarly, this dipole cancels with this dipole, and then this dipole cancels with this dipole, and so the molecule is nonpolar. All right, and that's got very special properties because it's nonpolar. The next one is xenon F2. We haven't done that one yet. So let's do that one. We got xenon with 1, 2, 3, 4, 5, 6, 7, 8. 2 bonds to fluorine. 3 lone pairs, so that's 5 groups of electrons. So, draw your triangle. And you guys are going to go, oh, do I have to draw the triangle? Can't I do it this way? This is just it's a way that works pretty well. I would say draw it this way. So you can already see it's going to be nonpolar because this dipole cancels with that dipole. And then the last one was ClF3. So this one, chlorine, 1, 2, 3, 4, 5, 6, 7. 3 bonds to fluorine, 2 lone pairs, okay, then again you're going to need your triangle. This is the one that's going to be T-shaped, right? $90 degrees. All right, now the dipole analysis here. This dipole cancels with this dipole, but this dipole does not cancel. There is some kind of an effect with the lone pairs, but it's not like a full electron bond. It's not like a full bond. There's no like net dipole. Don't worry about any of that. Just assume that the lone pairs don't have any effect at all. You know, OChem, you're going to learn that it does have a little bit of an effect, but it's not a full effect and it's not canceled. This molecule is going to be polar because this blue dipole here is pointing off to the right all by itself. It's not balanced by anything. All right, so you can predict whether molecules are polar or not once you know their VSEPR shapes. All right, let's see. Another comment to make here is sometimes students on a test will see that's one that we just did, ClF3. It might be easy to just look at that and say, well, okay, 3 bonds, it's got to be planar triangular. But it's not, okay? It's not at all. It's T-shaped, right? And you don't know that unless you have done your Lewis structure, right? And students make this mistake all the time. And usually if you got a whole set of these you're working on, usually there's more than one, for which if you had not done your Lewis structure, you would not have come up with the correct structure. You would have come up with some other thing that, let's see, the other example would be one with 4 Another example here might be, what was that one with the, let's see. Let me see here. So SF4, okay? So if I had said SF4 on a test, you might say, okay, that's got to be tetrahedral because, oops, erase a little bit too much there. You might say this is tetrahedral because it's got, you might do that. You might tell me it's 109.4. But the answer is no. And it's not. It's got 5 groups of electrons. This is the one that ends up being the seesaw. So this one is seesaw, not tetrahedral. All right, so then let's see. I think there's another slide here. Oh, okay, yeah. Let me see. There's 2 more slides. More slide. Okay. Let me get rid of that. Okay, perfect. So this is enough to give you sleepless nights. But have no fear, we're going to dissect this thing in the next video. But for now, we have learned that there are these categories. Right? 1, 2, 3, 4, and 5 categories. Then the first category has 2 groups of electrons, second category has 3, third category has 4, 5, and 6 like that. The main geometry or the electron pair geometry is the way you would draw them: linear, trigonal, planar, tetrahedral, trigonal, bipyramid, and octahedral. The name of the shape is based on the fact that you're ignoring the lone pairs, you're just looking at the bonds, and then you get a variation. So you have trigonal, planar, or bent. Here you have tetrahedral, pyramidal, and bent. Trigonal, bipyramid, seesaw, T-shaped, linear, like that. So this is where all the interesting stuff is. On the next video, we're going to learn that all this information correlates with the type of hybrid orbitals. And if it's linear, there's going to be 2 sp hybrids. If it's trigonal planar, there's going to be 3 sp2 hybrids, 4 sp3 hybrids, 5 of those. So that's the topic for the next chapter. So we'll end it here. Stay tuned.